Hello my dear friends, hope all of you are doing well in this difficult period of time. Welcome all of you again in our YouTube channel Invisible Threads. Please be safe by maintaining the proper COVID protocol. So today in this video I will discuss about the electrostatics of the conductors, the mobility of the free electrons for the conductor that made them conducting for the electricity. So let's begin. So our first topic of discussion will be on electrostatics of the conductors. So as we all know that the metal has the free electrons and the electrons are revolving around the nucleus and the attraction energy is very low in between the nucleus and the electrons, the outer shell electrons, because for the distance in between the nucleus and the electrons. So the electrons are the free and they can move without any pulling behind them, and we can say that they form like electron gas or the electron cloud. So the free electrons are free within the metal but not free to leave the metal, because there is maybe some small attraction in between nucleus and the electron, but for that the electrons cannot leave the metal and thus they form an electron cloud or the gas, and the electrons collide with each other and also with the lattice ions randomly. So suppose you can see from the figure there is a conductor. I am applying some voltage source here. It means I am applying the electric field here in this direction. You can see the direction of the electric field, and you can see the current will pass in this direction but the electron will move in the opposite direction of the current. So when there is no external electric field, the electrons are in continuous random movement through the surface of the conductor. With the presence of the applied field, you can see that the electrons drift against the direction of the field. It means the electric field acting in this direction and the electrons are moving in the opposite direction of the applied electric field. So we can see that when there is no applying external bias source, so there is no net motion on the conducting electrons along any particular direction. If there is no voltage source, there is no net motion, and we can say that the conductor is in electrostatic equilibrium. So the conductor carries no net current. We can also say that at this position the conductor is said to be in electrostatic equilibrium at this position when there is no externally voltage source applied to the conductor. So we will discuss now some of the properties of the conductors under electrostatic equilibrium. So the properties of the conductor under electrostatic equilibrium. So suppose we can take one conductor, maybe neutral or a charged one. As I have discussed already that under electrostatic equilibrium there is no drift or any kind of external force acting on the free electron. So suppose we assume that our statement is not true, and we assume that there is some non-zero electric field everywhere in the conductor. There is some electric field on the conductor, and so in the presence of the electric field, as we all know, there will be some net force on the mobile charge, which is the electron for the conductor. So now the definition of the electrostatic equilibrium, it means there will be no net force acting on the charge carriers, but we assume that there is electric field. If there is electric field, there will obviously a force on the moving electrons. So what we assume in the beginning is false. So we can write that the electric field is zero everywhere inside the conductor. This is true regardless the conductor is solid or hollow. It means either the conductor is solid one or a hollow one. It means having some space inside. So the electric field is zero everywhere. So now suppose I placed one conductor in the electric field of E. You can see from the figure I placed one conductor in the external electric field E. So due to the presence of the electric field, you can see that the electron will move in the opposite direction of the electric field. You can see the electron will move, the electric field is acting in this direction from left to right. The electron will move from right to left and get accumulated in this part of the conductor, and the positive ions will be accumulated in that part. So as the electron get stored in one place, there will be realignment of the free electrons, and there will be generation of an internal electric field. There will be generation of the internal electric field which acts from right to left, and the external electric field is acting from left to right. The internal electric field increase until the external electric field and the conductor reaches the electrostatic equilibrium. So in the equilibrium process we can say that the internal electric field will be equal and opposite to the external electric field. So our second point will be like, in the presence of an external electric field, there will be equal and opposite internal electric field generated inside the conductor. It means the electric field is equal to minus of E internal. So suppose now, considering the direction of the electric field on the surface of a conductor, we consider, suppose now we consider this is a conductor and the electric field is not, suppose the electric field in this direction making an angle theta with the horizontal line. So in this component, this is E cosine theta and this is E sine theta. So we can see that the free charges on the surface of the conductor will experience some force, because this is a component of the electric field along the horizontal direction. It means on the surface of the conductor, so there will be some force acting on the electrons and the electrons will tend to move. But this is against the definition of the electrostatic equilibrium, because with the definition of the electrostatic equilibrium, what we have learned already, that there will be no net force acting on the electrons. So the component of the electric field, it will be, the electric field will be obviously every time will be perpendicular to the conducting surface. So at the surface of a charged conductor, the electric field must be normal to the surface at every point. Now, so this is our third properties for the electrostatic equilibrium. So now we can consider one arbitrary shaped conductor, you can see from the figure, and I draw one Gaussian surface inside the conductor which is very close to the surface, you can see. And now we have already discussed that the electric field is 0. You can see I have written here that the inside the conductor the electric field is 0. So if I use the Gauss's law, you can see that the closed surface integral of E dot ds is equal to q enclosed by epsilon naught. This is the, from the Gauss's law we can get. And the electric field is 0 inside the conductor. It means the left hand side of the equation is 0. It means the right hand side should obviously be 0. So q enclosed is equal to 0. So we can get that there is no net charge inside the conductor. If there is some charge inside the conductor, it will obviously get distributed in the surface of the conductor. There is no net charge inside the conductor. The charges must reside only on the surface of the conductor. This is one of the properties. So now, as we have already learned that the electric field is 0 inside the conductor and it has no tangential component on the surface. You can see here I have already discussed that it has no tangential component. So there will be no net work done to move any charge from one point to another under the electrostatic equilibrium. So the potential difference between any two points inside or on the surface of the conductor will be the same. So we can write that the electric potential is constant throughout the volume of the conductor and has the same value on its surface. So what is the value of the potential on the surface of the conductor? It is the same inside of the conductor surface also. So the electric potential is constant throughout the volume of the conductor and also it has the same value on its surface. So now we will try to understand the value of the electric field at the surface of a conductor which is charged on. So from the Gauss's law you can see the electric field, the number 6 point, the electric field at the surface of a charged conductor. So you can say I have drawn one arbitrary shaped conductor here and I have chosen one short cylinder and it is my Gaussian surface here. So you can see that the short cylinder with flat area of delta S, and some part of the cylinder is over the conductor and some part of the cylinder is below the conductor. It means inside the conductor. This is our imaginary Gaussian surface. So the flat area is delta S and the negligible height, and the height is very negligible, and sigma is the surface charge density of the conductor. So the electric field contribution comes only from the flat surfaces, because for the flat surface only electric field and the normal to the surface is either parallel or the anti-parallel. It means that theta value has either 0 degree or minus or 180 degree. So for the two flat parallel surfaces, the total flux will be E delta S, because E and delta S is either parallel or anti-parallel. So from the Gauss's law we can say, and also the Q enclosed what it will be, because sigma, you can see from the figure that the sigma is the surface charge density. It means the charge per unit area. So the flat surface has the area of delta S. So what will be the Q enclosed? It's sigma delta S. I have written the magnitude here. It means for some cases the sigma can be positive, because the charge density is positive, and for some cases sigma can be negative. So from the Gauss's law we can write that the E delta S is equal to mod of sigma times delta S divided by epsilon naught. So the magnitude of the electric field will be mod of sigma by epsilon naught, or we can write it in the vector form as E vector is equal to sigma by epsilon naught n cap. So if sigma is for the positive charge, there the sigma is greater than 0, so the electric field will be acting outward from the conductor, and if the charge is negative, the sigma will be less than 0, so the electric field will be acting inward for the negative charge density. So up to now we have seen the property of the conductor from the view of the electrostatics. So now suppose I want to make a region in space free from the electric field or any of its partial components. So from our experience in daily life also, we can see that during the lightning thunderstorm it is advised to stay inside the car and not under the trees or in the open ground, because the car has the metallic body of the car and it acts like the electromagnetic shielding from the lightning. So the metallic body will shield us from the electricity with the nature it has. It's called the electrostatic shielding. So what is electrostatic shielding? Suppose this is a conductor having some cavity inside. So if the charge density, there is some positive charge there, so and the charge density is greater than 0, so I have already discussed that the electric field will be acting outward, and if the charge density is less than 0, the electric field will be acting inward. And if there is a cavity or any space inside the conductor, I have already discussed that the electric field is 0, and inside the cavity the potential is a constant. So no charges inside the cavity, because if there is some charge is there, it will get transferred in the surface of the conductor. And electric field is 0 inside and independent of the shape of and the charge of the conductor. So electric field does not depend on the shape or what is the charge density on the conductor, and all the charges will be there on the outer surface on the conductor with the cavity. So if there is a charge, maybe some charge is there inside also, but it will get distributed over the surface of the conductor. So we can write that whatever the charge and field configuration outside, any cavity inside the conductor remains shielded, because if I put some thing inside this cavity, maybe some sensitive instruments or some instruments like that which I need to save from some action of the electric field, so if I keep them inside in the cavity, you can see that it remains shielded from outside of the electric influence. So because the total electric field inside the cavity is always 0, this phenomena is called the electrostatic shielding, because sometimes we need to protect some sensitive instruments from outside the electrical influence, and if we make some cavity inside the hollow conductor, and if we put those things inside this cavity, so there will be no influence of the electric field from the outside. So my friends, I am concluding my today's discussion here. Hope all of you are following invisible threads. If you have any kind of problem or any suggestion for me, don't hesitate to let me know in this video's comment section, and I will be really happy to help you. Stay motivated and stay safe. Thank you.